So, a couple of questions first. Does anyone have access to any CNC machinery at their workshop or in their hack space? Who's got a laser cutter? Who's got access to a CNC mill or router? Slightly more laser cutters, maybe? Does anyone who thinks that laser cutters are better than CNC mills? Who thinks mills are better than laser cutters? Yeah. I don't know. The reason I got a, I've got, like the last talk, it's quite link heavy, and I know I don't have much time. So I've got a short link up here that will take you to this presentation, and then you can click on any of the links that you found interesting later, and I'll be showing this slide at the end as well. And the presentation is going to cover a bit on hardware, a bit on tooling, a bit on software, and then some of the applications that you can do with CNC mill. And although this talk is billed as CNC milling with Linux, after doing the research for the talk, I realized almost all of this stuff is open source, cross-platform at least. Because I use Linux, all that stuff is true. So all the stuff I'm showing here, you could also use on Windows just as well, or any other platform. So the tools I started with, I bought a CNC router to start with, on the left with the 400 mil bed size, because I couldn't afford a laser cutter. And I thought I was getting something not maybe quite as good, but through using it, I've learned that there's quite a lot of stuff that you can do with a CNC machine that you can't do with a laser cutter. And more recently, I've got this mill here on the right, but it's really good for metal and very high precision stuff. The difference between a mill and a router is that a mill is usually much more rigid and will be able to handle harder materials and is more precise. A router will usually work faster, but you'll only really be able to use it for woods or plastics. And I'm a bit of a believer of buying second-hand UK tools rather than brand new, cheaper tools, because I think you get a better deal by getting that Denford mini mill is maybe 10 years old, but it is built like proper old school English stuff. So machine control, after you've got your machine, you're going to want to plug it into a computer so you can control it. The thing to use is LinuxCNC, which is an awesome platform. I thought this talk was going to be quite a lot about LinuxCNC, but there's not much to say about it apart from it is totally rock solid and reliable. I've never had a problem with it. You should definitely use it. It comes on a, I'm not quite sure, the resolution looks quite bad on this, is it? Can people see the pictures and things like that? Good enough. It comes on a live disk, so that's been optimized for real-time usage. So when you're generating the signals that drive the stepper motors, you want them to be really precise, so you get smooth movement. And it comes as a kind of CD that you can boot, and then you can install it if you want to make that change permanent, but you can also just try it out. One thing I also wanted to mention was this kind of hardware version, GRBL, which is to run on the AT Mega stuff like an Arduino. And that has got stepper motor drivers, and they've built some really cool firmware that runs on that makes use of all the timers, and then you get a real-time milling controller. So that's more like the kind of the 3D printer stuff where everything is embedded on one control board, and you can do the same there. And you can buy a shield that will do all your motor control. If your mill is small enough, if you're doing something really big, you probably need much bigger stepper drivers. Most of these, the cheap way to do it is to use just a parallel port on an old PC. That works really well. But be careful about what breakout board you use. The one that I bought, one of the buffer chips didn't even have its VCC connected, and it took me a while with a scope to find that and fix it. So I would say save yourself the bother and buy decent stuff. Don't buy just the cheapest stuff you can find. It kind of depends on your mentality, but the reason I bought my machines rather than building them was because I wanted to get on and be using them and learn how to use them rather than spend 2 years on the process of learning how to build a CNC milling machine. But that is completely user dependent. After you've got your machine, it's really worth going through some processes to make sure you can get the most out of it. So make some measurements from the machine, calibrate it, find out what your run out is, which is how much your spindle is moving as it's turning. These things are really going to tell you what kind of level you can work down to. If you've got quite a lot of run out on your spindle, then you're not going to be able to do great PCB stuff or fine pitched routing stuff. If you've got a lot of backlash, so when you drive it forwards and backwards, it it doesn't move, then you can compensate for that in software, but only if you know how much it is. So you should invest in a dial gauge and some vernier calipers. Have an emergency stop button handy. I've never had a dangerous accident with my machines, but I've saved myself a lot of money on broken tools because I've told the machine to move somewhere and I've realized it's going to snap the end of the tool off unless I stop it quickly. And having that big red button you can just hit really easily is the difference between saving the tool or smashing it. Safety specs are good for that as well. And I always keep a can of WD-40 for lubrication if I just realize that the thing's going to melt and I need to quickly cool it down. So on to tooling. If you're used to things like pillar drills or cordless drills or whatever, you're used to having a chuck that can take any size bit, but the way that milling works is you usually have a specified shank size and then you get a range of tools with that shank size. So if you're, say, doing PCB work, pretty much the standard is 1/8 of an inch. So you need something that is going to hold an 1/8 of an inch, and it doesn't matter what size your drill bit is, it's always going to fit in 1/8 of an inch. And those things are held in these collet sets, which are kind of like a chuck that has a very small amount of give. So it will go from 1 millimeter to 1.5 millimeter, and you can tighten that up. What I've found that you get pretty poor run out if you're working at the extreme end of your collet. So if you've got a 1 to 1.5 mil collet, and you're trying to clamp a 1.5 mil bit in it, no, a 1 mil bit, the smaller size, you're having to tighten it up a lot, you'll get bad results with that. So for the PCB stuff that I'm doing, I'm using 1/8 inch stuff. I'm not using a 3 mil collet tightened up. I just ordered an 1/8 inch collet, and then I get really low run out on that. And there's an enormous learning ahead of you if you want to get into this, to do with how fast you run these tools, how long they last, what kind of chip sizes you're getting out. You want a lot of chips because the chips is what carries away the heat from the process so that you don't melt your materials. And there's a link, an unreadable link down there that you'll be able to read if you checked it out on your computer later. That's got a really good starting point for getting started with feeds and speeds, and that's one of the big areas that you have to just learn through experience and what works and what tools you've got. I've bought a lot of cheap tools off car boot sales, and usually I don't even know what they're made of. I just have to keep trying until I find the material that they work with and keep them stashed away and keep some notes. I've got a big table that I've shared in a Google document, so if you're getting started, you can refer to that for some starting points, but also this link is like the beginning of a large tutorial about feeds and speeds. One of the great things about a laser cutter is you can just slam your material in, close the lid, press go, and then 10 minutes later it's done. If you're milling and you're cutting, and especially with harder materials, stuff needs to be clamped down. And I had a lot of accidents to start with where I'd got like 90% through a 3-hour job, and then on the last cut, the material moves and the whole thing is screwed up. So you really do need to clamp properly. The best solution that I've found is to use this T-slot system. It's pretty standard in engineering on the bigger machines. You just get these kind of upside down T-shaped slots in your bed. These bolts fit into them, and then you can use some cool step clamps. I might just zoom into that so that you can see that picture. So you've got this little triangular bit with lots of steps on it, and by moving the thing on the left up and down, you can get a very parallel, very tight and strong connection and secure your piece to the work very well. So moving on to software. Starting off with the kind of traditional route of designing a part in some kind of CAD program. Here's some open source ones. QCAD's decent. It's kind of got an old school style interface. Will appeal to some people. A more modern thing. I mean, Inkscape is more of an illustration package, but pretty much anything that can export vector files you can use for design. If you've had any laser cutting experience, you probably know that. There's a little bit of work to do in between getting your vector files into a format that the machine can use, but once you've worked that out once, you usually can then automate it. You don't have to spend any more time doing it. OpenSCAD is really good. Most people think that's just for 3D printers, but I've used it really successfully with my milling machines. I've written a little tutorial on how you can make a little case like this one, starting off with a model, and it's quite nice. As a programmer, I really like being able to type in where all my bits are and then create a case that is exactly the right size for it, and then if I need to change something later, the case can just change. I don't have to go back and edit loads of files. So you can use some CAD programs. There's lots more out there. I just chose some freely available ones to make your designs. And then a really important part is toolpath generation. So you've got your outlines, but now you need to turn that into what a machine can do. Usually with a laser cutter, you're just doing one outline and that's the end. But if you're cutting, say, 5mm aluminium on a smaller desktop machine like mine, I'll do that in maybe 10 passes, cutting out 1/2 mil at each time. So I need to have a program that works on my vector files and then turns that into a toolpath. Or if I was doing something in 3D, I'd need to be kind of creating a scanning toolpath that is moving my tool head, and probably I'd do that in 3 different goes. I'd use a really big roughing bit to really quickly make the outline, and then I'd move to a smaller bit to get closer to what I want, and then a really fine bit to get super high detail. PyCam is free, but it's kind of a bit dead. It's not had any development done on it for about a year. There's lots of unanswered questions in the forum. There's really not that much out there for open source toolpath generation. It's very, very expensive business. I spoke to a guy who installed Jaguar robots in their manufacturing plant, and he said it's really the software that costs the money, not the robots, which kind of blew my mind. I always thought it was the other way around. But all that kind of specialized toolpath software is a bit locked up in their kind of protected IP world at the moment. There's not much out there for open source stuff. So if you fancy getting involved, there's a lot of a need in toolpath generation. Mentioning Kanban, it's not free, but it's developed by one of the Bristol Hackspace guys who I know, and I know a lot of people who do use it. That's for Windows, but there's a Linux version just coming out now. Some other stuff that I think is really cool is building your G-codes yourself or doing post-processing of G-codes. So G-codes look like this. These are the kind of the instructions that you'd feed into into something like LinuxCNC, and it's a text file. So if you're a Unix or Linux fan, then this is brilliant because everything is about manipulating text files, and you can just use your command line utilities to mess around with these stuff. It's very easy to write parsers in Python or whatever your preferred scripting language is. I wrote a little program here called drillpick2, which lets you load in a bitmap, and then it creates a file that is going to turn that into a series of movements on your CNC machine to kind of carve these carvings out. It's a bit difficult to see, but this is black plastic with a very thin white layer. And so by moving the bit along and by syncing it up and down, I can create an image from it that looks really good from a distance, but when you're close up, it's easy to see how it's being fabricated in that way. You can do it with drilling or by scanning. CNC Boxotron, someone made this thing called Boxotron I found on Thingiverse, which is for making little boxes. You just type in, I want a box 50 by 20 by 100 mil, and it'll generate the parts for you. Very straightforward, but it doesn't take into account kerf, which is the thickness of your cutting tool, which is pretty much ignored in the laser cutting world, but when you're cutting with a 3 mil drill bit, you've definitely got a 1.5 mil. You'll be missing 1.5 mil after you've cut it out. So CNC Boxotron takes into account kerf. That's available on my GitHub. And there's a bunch of other G-code generators that you can have a look at that kind of generate drilling matrices or creating speaker grills, loads of holes tightly packed together. One I just found, G-code Ripper, that can wrap flat things around curved shapes, which is really interesting. And you can kind of map a surface and then wrap a flat thing around a curved object. You can do some cool XY alignment, which was mentioned by the guy who was on previously about the fiducials for lining up PCBs. I stuck a webcam on the bottom of my CNC mill, and then by locating the parts on my PCBs or anything else I want to put back into my machine and work on, I can find where those features are and then get my software to automatically reposition all the G-codes so that it's drilling exactly where the holes are. Got some links there for you. And another thing that you might have problems with if you're doing stuff on PCBs, because you're working on very thin layers of copper on the top and you're working on very fine bits, you need to be working relative to the top of the surface really, rather than relative to the bed. And because FR4, this kind of PCB material, is usually a bit bent, and especially if you're clamping it down, there'll be bits that are slightly higher in the top and bits that are a bit lower around the bottom. So one thing you can do is attach a crocodile clip to your drill, have a little metal plate straight on your copper board, and then do a kind of XY scanning and probing, generate a depth map of your bent PCB, and then wrap all of your etching parameters around that bent PCB, and then you're etching according to the top. And that that is the difference between a usable SMT homemade board and something that is completely hopeless. So if you're doing PCBs, especially with fine pitch stuff, definitely look at that. It's pretty much impossible to do it otherwise. And here's an example of using that program gcode ripper to take a flat thing and then wrap it around a curved shape. So that's kind of doing something similar but more decorative. OSHCamp I found quite recently, or OpenScam. It's all about ripping you off but being honest about it. It lets you see your toolpaths after you've made them, which is really fantastic. So you can make something, and I've made stuff. I'll put it on the machine. I haven't really been aware of what it's going to do, and then the machine does something unexpected, like going straight through the bed or going up to the top or going off the outside or something. And OpenScam lets you look at what your toolpath's going to do and model it and play it forwards and backwards and find mistakes, which is really good if you're writing programs that generate G-code yourself. So I've got 2 minutes and 37 seconds to talk you through some quick applications, because there's a lot of stuff you can do. You can do PCBs. You can do some really interesting Veroni-style splitting up of edges to get very fast PCB manufacturing times instead of the kind of etching stuff. You can make really nice cases. I've got a nice little photo of my homemade Tesla coil here, and something I made for Sustrans. It's quite nice that you can do engraved stuff and have all your sockets mounted really nicely. It's the difference between a homemade looking project and a really professional one. General cutting, again, I'll relate you to that feeds and speeds document I've got where I've been documenting my own process. This is cutting out some aluminium for a drawing robot. You can do gear cutting if you add a fourth axis. Usually what you do is you unplug your y-axis, you plug this into the y-axis instead, and then you use a program like G-code ripper to wrap the y-axis around a circle, and then you can use that to do gear cutting. You can do some really interesting stuff with probing, not just for getting things flat, but this guy uses it to do very fine micro capturing of shapes. This is a coin from New Zealand, and then you could then load that up and do some manipulations on it or cut out a bigger version of it. A friend of mine made a photo microscope. He stuck a little USB microscope on a gantry and then moved it in little steps and then stitched all those images together. This is an image of the crystallization of chocolate. You can do some cool drawing, take out your cutter pit and then make a little Sharpie holder and do some really fantastic kind of old school Roland XY plotter stuff. Stencil cutting, using a drag knife, cutting paper or vinyl, grip tape, that kind of stuff. Printing, this is the thing that I made that drill pick for because I want to have a go at cutting MDF, then rolling ink onto it and then pressing it into paper. This is a really beautiful example of that. This was done on a CNC router on MDF. And I've saved the best bit, the most inspiring bit for me at least until last, which is something I completely blew me away, which is using your CNC machine to make a mold and then casting hard plastic resin parts out of that mold. So you get the beautiful precise finish of a CNC machine, but in a fast, reproducible way of doing casting with plastics. So you cut out, using very fine bits, a negative mold in a very soft, special modeling material. Just have a look at the detail on this. This is a planetary gear setup. You pour it full of flexible silicon, and then you pour in your resin parts that you can color, and you can make these amazingly fine working parts that are custom and your own thing, and they work. It's amazing. So this guy has got a blog post. He's written a whole a really enormous, in-depth tutorial on how to set up your milling machine and how to do this process. And I've used quite a lot of his links. I've used his techniques to setting up my own milling machine. And I'd really recommend his documentation for getting the most out of yours. I followed this process of using this to create things, 3D shapes with resins and hard resins. There's quite a lot to it because casting turns out to be a whole massive process you have to learn all about as well. And just finding the right types of resins and silicons is quite difficult. But you can see the results that are possible if you want to get into it. So that's where I'm going to leave you. Thanks very much.